Capacity analysis for an assembly line. In this video, we're going to consider a high-end kick scooter called Xutr by a company called Nova Cruz. You see a picture here on this slide of the product. And on the right, we also see the weekly demand as it changed from March to January the following year. One thing to keep in mind is that the company didn't know, let's say in March, they didn't know what the demand will be in the following months. So they couldn't anticipate it. They could maybe have some reasons to believe it will pick up, but they couldn't know the magnitude of this demand in the following months. So suppose this is now March. The company has demand for 125 scooters per week. Right, so would like to produce 125 scooters per week, not more. They decided to assign 3 workers to and have an assembly line system to produce the scooters. And the way they divided the activities, right, there is something like 80 parts that they need to attach, and so they divided the work into station 1. The tasks assigned to this station were taking around 13 minutes per scooter. Then there is station 2, which did some additional assembly tasks for 11 minutes per scooter. And then station 3 was doing some finishing activities and testing, and it took 8 minutes per scooter. So you see the process flow diagram here with an initial inventory of some parts, station 1, then some work in progress inventory, then station 2, then work in progress and station 3, and then finished scooters inventory. And I hope you see that this is just one way of producing the scooters. There are many other ways. For example, they could have those 3 workers work separately, each of them on a complete assembling a complete scooter, right? And there are other work arrangements. Why did they organize it like this? First of all, if each worker makes a complete scooter separately, then there are some disadvantages. They have a lot of activities to learn, and so therefore learning, the way they learn, the speed at which they learn is slower. So they don't become as efficient as they could become when they only learn a few activities each, right? In big assembly lines where there is, let's say, cars are made, you have a very large number of stations, and each worker does just a few parts or even attaches just one part, and then they learn much faster how to do their activity much better and become much faster at it, and also do a better job, probably from the perspective of quality. The second thing is also investment in some kind of equipment. So how much capital has to be invested in equipment or in some machines that those workers use, right? So if those workers use, for example, some drills or other equipment, maybe not all of them require this equipment because, right, drilling might be necessary during assembly, but not during final steps or testing, right? So you don't need 3 drills. You need just maybe 2 or 1 drill even, right? And some additional equipment could be assigned selectively. So you have some saving in terms of investment in equipment. Now, one thing to realize is that this imbalance of time, 13 minutes, 11 minutes, and 8 minutes, was probably not by design. They didn't intend to have more work for worker 1 and so little work for worker 3. The management probably tried to balance it as much as possible and maybe applied some logic like, this is just final testing, right? But as the workers learned to do their activities, they actually became better at some things and not as good at other things, right? Maybe some activities have to be done very carefully in order not to introduce quality problems. So maybe over time, when the time of each worker's activity was measured, they found out, it takes actually much more on station 1 than station 2, and then even more than on station 3, right? So this was not by intention. This might be basically the result of some initial division. Assembly, now, in the assembly line, we are still interested in finding out what's the capacity of this assembly line, how quickly this assembly line can produce scooters. So we can do our analysis as we did before. We can basically say what's the capacity for each station, and we can calculate it as number of workers per total activity time for one scooter, right? So since we have one worker on each station, this calculation will always be 1 divided by something, and this something will be the time per scooter on each station. And right, since the times are decreasing here, the largest is on station 1, then the smallest capacity will be on station 1, right? It's 1 over the largest number will give us the smallest capacity. Here is the conversion from scooters per minute, which is fractional. It's easier to look at scooters per hour, right, which is a bit larger. And so we see the smallest capacities on station 1. So when we calculate the capacity of the whole assembly line, which we, because it's still a linear system, we can calculate as minimum of the 3 capacities, we get 4.6 scooters per hour. And if you convert it to scooters per week, assuming 1 week is 35 hours, you get 161 scooters per week. So obviously, station 1 is the bottleneck, because when we were calculating this minimum, it's the capacity of station 1 that was the minimum. Now, if the demand in March, remember we're in March, is 125 scooters per week, then it is reasonable to make minimum of capacity and demand, which is minimum of 161 capacity and 125. So that's 125 scooters per week. So we're basically producing at the rate of demand. The process, because the process is demand constrained, again, in this minimum 125, the demand is the minimum value. And that means also that we can say that one scooter should be produced on average every 16.8 minutes, right? So that we can actually invert again the flow rate, as we did here with capacity. We did 1 over activity time, then we went to flow rate, from capacity to flow rate, and then when we invert the flow rate, we get again activity time, but this is like an available time for each worker to complete each scooter, right? So essentially, each worker will have this much work, 13 minutes, 11 minutes, and 8 minutes, to be done within 16.8 minutes in order to match the flow rate to the demand, 125 scooters per week. Of course, the workers are capable of working faster. They don't have to spend 16.8 minutes on each scooter. They just can, right? But they could work faster. How fast can they work? Well, so this is important to realize that they can, each of them has different activity time, but overall, they will not be able to work faster than spending 13 minutes for every scooter. What's the reason for this? Well, if worker 1 needs 13 minutes to get this picture, 13 minutes for each scooter, then station 1, right, will finish 1 scooter after 13 minutes and start working on the next scooter. That means that station 2 will not get its input, right, faster than 1 every 13 minutes. And because of this, even though it finishes the scooter in 11 minutes, it will have to wait 2 more minutes for the next scooter to arrive, right? And then station 3 will again finish its work every after 8 minutes, but then it will have to wait for this completed scooter from station 2, and these will be again arriving 1 scooter every 13 minutes, because station 1 will set here the pace. It's the slowest. We could say it's the slowest station. Now, what if the bottleneck was not on station 1, but on some later station, let's say on station 2? And let's say station 1 would be taking 11 minutes and station 2, 13. This would be inverted, right? Then what would happen is station 1 could potentially produce scooters faster. But if it did that, it would just create a buildup of inventory here in this inventory here, right? And that wouldn't really make any sense, because over some weeks, you would just have a lot of partially finished scooters here, which would just be a wasted effort, because station 2, which would be the bottleneck, wouldn't be able to process all those, right? So on average, it only makes sense that station 1 works at the pace of the bottleneck, right? If assuming we want to work with a cycle time of 13 minutes. So going back to our example, right? Cycle time, we can say desired cycle time is 16.8 minutes, but we can work even at 13 minutes per scooter, right? And not faster, because if you try to work faster, station 1 would not be able to process those scooters. So an interesting question we can ask is, what is the time to make X scooters? So for example, suppose, right, this demand is actually arriving as orders from our customers, and one customer just ordered 20 scooters, and we want to make those 20 scooters as quickly as possible, because we at the moment have nothing in our finished goods inventory. So the first thing to realize is that it's important to know whether the system is already working. If the system is already working, remember, every station gets a finished scooter pushed forward once per cycle time. So this last station will also finish the scooter every cycle time. So if we need X scooters, we need X times cycle time. But that is when the system is working. When the system is empty, right, what happens is that um, the the first station will, if all the stations are empty, first we need to get one scooter through first station, and during this time, when station 1 is working, station 2 has nothing to do, because there is no partially finished scooter for it, right? So station 2 will have to wait for station 1 to finish its work, then it will start working, and then when it's working on the first scooter, station 1 will start working on the second, but the first one is still on station 2, right? And then after station 2 is done with it, it moves it to station 3. And when station 3 is done with it, this is when we have the first scooter completed. So when the system is empty, the time to complete the first scooter is the time that it takes to get the scooter through all the stations in the assembly line. And then every following scooter will take a cycle time, because then the station is actually fully operating. Every station has, the assembly line is fully operating. Every station has a partially finished scooter on it, right? So if the system is empty, we need to see time through empty process for the first scooter to be made, and cycle time for every unit after the first one, right? So X minus 1 times the cycle time will be the time for the remaining units, right? Now, there's again the differentiation if it is a worker-based line, like the one we have here, right? When workers just move physically the scooters to the next station, probably they are next to each other, so they just leave the scooter on one side of their station and the other worker picks it up. Then we can say that time through empty process is just the sum of activity times, right? So basically, the scooter will be finished after the total time of activities. In machine-based lines, when we have some kind of automatic mechanism to move products forward, let's say in long assembly lines like car manufacturing, usually those machine-based lines, they move the products on each station forward every cycle time, whatever cycle time is there. So even if the workers finish earlier, the product is not moved forward until the cycle time is finished. And in this case, the time through the empty process will be number of stations times the cycle time. The difference is small, but it is still visible, especially if the line is very long and highly imbalanced. So what's the time to make 20 scooters? Well, if it is a worker-based line, remember, it will take 13 minutes for the first worker, 11 minutes for the second, and 8 for the third. So this will be the time to make the first scooter, right? And then it will take 20 minus 1 times 13 minutes to make the every additional scooter. So each of those 19 scooters. And remember, this is assuming the cycle time is 13 minutes per scooter, right? This is, we're trying to make it as quickly as possible. So this calculation, if we want to do it, we will have 32 minutes plus 247. So that gives us 279 minutes, right? If you have a machine-based line, the difference will be that this will take, for each of the 3 stations, it will take 13 minutes, right? If you have a mechanism that automatically moves the products from one station to another, the mechanism will move forward each product once per 13 minutes. So to move through 3 stations, it will take 3 times 13 minutes. So the calculation here will be 39, not 32, plus 247. That will be 286 minutes.